But one thing I have just curiosity. In the diagram, you have shown the curvature on the both sides is the same, but in your figure, the curvature is much sharper. Not in the photograph.
This
much sharper. The lower curve is much sharper than
Yeah,
the upper
see,
curve.
again,
So
so
it means the stiffness.
True.
is
So it
changing.
depends which length scale we have gone. So I'll show you. So for example, if you go to the extreme parameters, your wrinkles start getting deformed. This is how it looks like. The rounding at the bottom, which is there in the sine function, is also lost. So basically, from the elastic instability or the creeping instability, where you have a permanent creeping deformation, at where the stresses are more concentrated at the very bottom of the polygon. And if you further increase the oxidation time or the strain, you get very deformed wrinkle shapes. So it all depends on your control. And this is okay. So this just I'm showing you a video just to convince you that this is reversible. So these are the video made with the AFM images. Again, each frame is a scan, and I'm stretching. So this is the strain. I'm stretching with the 5%, 10%, 20% strain, and with the 22% it becomes completely flat. And once you release them, it will go back to the complete morphology or the full maximum of the wrinkle amplitude. The same wrinkles you can make now also in the 2 dimension if you stretch in both directions. And now in the 2 dimension, because in 1 dimension you have to release only in 1 direction. In the 2 dimension it depends what is the sequence of releasing. If you release them firstly only in the x, so let's say I have stretched them 30 units in the x and 30 units in the y. That's initially stretching, and firstly I am keeping the y strain constant and only releasing it in the x direction. So firstly you will get the linear wrinkle because it's only 1 dimensional, and the moment you start releasing the y, you will get this nucleation of the perpendicular wrinkles, and eventually what you get